According to the quantum mechanics, the electron cloud for a hydrogen atom in the ground state has the following volume charge density as a function of how far you are from the center. Q is the charge of the electron, A the Bohr's radius. Find the atomic polarizability of such an atom, i.e. find alpha. Okay, so the way we can strategize this question is we know that alpha is buried inside the relationship, assuming it is a one-dimensional relationship between the dipole moment and the electric field. Okay, so I need alpha, so which means I would need the electric field. Okay, so and the way I'm gonna find the electric field, I'm gonna use Gauss's law. So if this is our sphere, right, and let's say I want the field here, then I would have to take a Gaussian surface here, right? And then I'm gonna apply Gauss's law. So this here is at a distance r, right? And I know that Gauss's law says integral of EdA is equal Q enclosed over epsilon, and I need to find out how much is enclosed inside my cloud, right, at a distance r away. So for that I would have to integrate the volume charge density rho r d tau on V, right? This is a sphere, so this would be Q over pi a cube, and this is going to be a triple integral of e to the minus q r over a, right? And so in spherical coordinates, this is r squared dr, and so if we call these r primes, because we need to integrate from 0 to r because that's where the Gaussian surface is, so let's use the dummy variable r prime here. So this is r squared r prime, and then d theta going from 0 to pi, and d phi, oh wait, we forgot sine theta, so there's a sine theta here, d theta going from 0 to pi, and d phi going from 0 to 2 pi. Okay, so now the sine theta d phi will give us a factor of 4 pi, so we get q 4 pi over pi a cube. Now as far as the r integral, you could do this by parts twice and you would get the right answer. I just used the Mathematica, and I got e to the minus 2r over a squared e to the minus 2r over a minus 2x squared minus r squared minus 2 ar minus a squared. Okay, plug this into Gauss's law. As usual, EdA becomes EA due to symmetry, spherical symmetry. So we get E, so back to Gauss's law now, E 4 pi r squared equal this whole thing divided by epsilon, so 4q over a cubed epsilon E, oops, wait, this is positive here. Actually, 1 second, I may have reported the wrong, no, that's not the right answer. This is, sorry, I copied the wrong answer to the integral. This is a, one moment, let me just evaluate the integral again really quick. Yeah, this is a cubed over 4 minus a over 4 2r squared minus 2ar plus a squared times e to the minus 2r over a. Okay, so we could cross out these 4's here, and going back to Gauss's law, we get a cube here cancels, and we're going to get q over epsilon into 1 minus e minus 2r over a divided by a squared, because we have a over a cube, so I foiled the a cube into it, 2r squared minus 2ar plus a squared. Okay, and then divide by 4 pi r squared to get the electric field. Now here's the thing, if the proton will be shifted to from r equals 0 to a point where the electric field will has to equal the external electric field will have to equal the electric field of the electron cloud, right? That's when R equals D, right? When R equals D, so then I would get, so replace R with D there and solve for E, so E will be Q over 4 pi epsilon D squared times 1 minus let me bring the a squared in, so this becomes e minus 2d over a, and this becomes 2r or d over a squared, right? Minus 2d squared d squared over a squared. So this is d over a all squared. So this is d over a plus minus minus, so this is a plus here, plus 1. Okay, and the reason I made everything in a ratio of d over a, because I know the separation distance is so small, so dA is much less than 1. So now I can expand. So we could do better than this expression. I could expand d over a, or e to the minus 2d over a in a Taylor series, right? So e to the minus 2d over a, make it a polynomial. We know from Maclaurin series for minus 2d over a, this is equal 1 minus x. So this is like saying e to the minus x, where x is 2d over a. So this would be 1 minus 2d over a over 1 factorial. Right? It's 1 plus x plus. So just so you know, I'm using here e to the x. This is the Maclaurin series for e to the x. 1 plus x plus x squared over 2 factorial. I'll write it here. Plus x cubed over 3 factorial, etc. Okay, it goes in that pattern. So my x in this case is minus 2d over a. So the first term will be minus 2d over a, and then plus x squared. So this will become positive here, and then this is over 2 factorial. So this is half 2d over a squared, and then the next one will be minus, because cube, 1 over 8. 3 factorial is 8. 2d over a cube, etc. Okay, plug this in, replace e to the minus 2d over a in the red expression, and we will get okay, 1 minus, okay, so this whole thing here plus higher order terms, and this is multiplying 2d over a squared plus 2d over a plus 1. Okay, and let's FOIL these up to the third order. So we will get e to be 1 minus, okay, so we get 2d over a squared plus 2d over a plus 1. That's foiling 1 over the second expression. Now I'm going to FOIL minus 2d over a, so I will get minus 4 d over a cube minus 4 d over a squared minus 2d over a. Okay, so now I'm on this third term here. So let me continue here actually. Okay, so now I'm gonna FOIL that, so 2 cancels the 2 and I get 4, so plus 2 squared is 4. This is gonna be a fourth order, so I don't really care about that, right? Yeah, I don't care about that. So let's go to the third order. So I'm gonna skip the first one. So then the second one will be half 2. I will get, yeah, here I will get 4d cube d over a cube, and then plus half 2d over a squared. Okay, and the cube term will give me a fourth order on the first, a fifth order on the first, I don't need, a fourth order on the second term, and then just a third order on the last, which I need. And then the rest will be higher order terms. Okay, so let's simplify this. So notice that this one here crosses with the 1 because there's a minus sign, and then I have let's collect these. So I have this and this squared. Actually, let's start with the d over a, those go away, and then d squared, I get this is gonna be 2 and 2. Notice that here I get 4 over 2, so 2 and 2, 4, and I have a minus 4 here, so these yellow ones go away, right? And the only thing I'm left with is the cube. So I have this here, and this here. So what are these? Minus 4. So minus 4 and 4, these go away, and I'm just left with 4 minus 1/4, right? No, 4 minus, yeah, I'm just gonna be left with E equals Q 4 pi epsilon d squared and then I've got minus this is 8 over 8 minus 1, and I have there minus 4 minus 1 minus 4. Oh, one moment, I realized something. Sorry, 3 factorial is 6, not 8. So this is 6, which changes things here, doesn't it? So this is 6. 6. So let's see how this changes things. So we get C.
By the way, if you actually calculate the electric field at the Bohr radius, you get 5.
So let me just run quickly and fix that sixth problem here. So where would that come in? That would come in on the last term only, where we had this. Okay, so now all I have left is that. So what's that? 8 over 6, which is 4/3 d over a cubed. Okay, so that's after expanding the exponential, and just cancel the d cubed with the d squared, and I get, let me go back to these colors, they're more natural. So 4 with 4, so I get q over 3 pi epsilon d over a cubed. Right, now keep in mind that the dipole moment is qd, right? So I could replace this with the dipole moment, and I get E to equal P over 4 pi epsilon a cube, and which makes P equal 4 pi epsilon a cube E. Now remember, oh, by the way, these are vector relationships, yeah? Remember that originally P is equal to alpha E, so this has got to be my alpha, so which I'm trying to get. So my alpha is 4 pi, wait, is it 4 or 3? 3, sorry, there's a 3 here. I wrote it as 4. It's correct up there, but I just copied it wrong. So 3 pi epsilon a cube. This is my atomic polarizability when considering the quantum mechanical model. This concludes this question.